días a todos. Estamos en el acto de presentación de la tesis Propagation, Localization and Navigation in Tunnel-like Environments, que será presentada por Carlos. El secretario leerá la normativa del acto.
Bueno, el acto de defensa de la tesis consistirá en la exposición por el doctorando de la labor realizada, la metodología, los resultados y su discusión y las conclusiones, con una especial mención de sus aportaciones originales. El tiempo de exposición no excederá de 1 hora, salvo que el presidente estime oportuno ampliar dicho plazo. Al término de la exposición, los miembros del tribunal formularán al doctorando cuantas cuestiones estimen oportunas. Asimismo, los doctores presentes en el acto público podrán hacerlo en el momento y forma que señale el presidente del tribunal. El doctorando dispondrá de un turno de palabra para dar respuesta durante el tiempo que prudencialmente indique el presidente.
Tiene la palabra.
If you allow me, I will do the talk in English. So first, thank you very much to everybody and to the jury for accepting the invitation. And I'm really excited and glad to present you the work we have been done during these 4 years of PhD in the robotics group, entitled Propagation, Localization, and Navigation in Tunnel-like Environments. Quite straightforward. Under advisory of Drs. José Luis Villarroel and Francisco Vera. So I will give you a little introduction and motivate the talk, and talk to you about wireless propagation in tunnels, and how can we navigate in these scenarios founded in the communications aware context. Then a brief history of propagation in pipes, and how can we exploit this phenomenon through lights. At last, I will summarize the talk and talk to you a little about the challenges we face in this work. So the goal of service and rescue robotics is to perform tasks that are phdthesis or impossible for humans. For example, inspections in small or dangerous places with chemical disaster, or response in event of disasters. To perform this task using a multi-robot team yields better results than using just one robot. It gives robustness to the system while reducing the time to complete the task. In order to cooperate, the robots must exchange information about the current state and stream other relevant data such as video, images, voice. And to achieve optimal or secure communication, propagation in the environment must be known. So in this context, our research group is participating in 2 projects, the SEO and Teloman, which use team of robots for service, security maintenance, and environment monitoring. They are particularly interested in tunnel-like scenarios, which are tunnels, mines, or pipes, such as others are as the Army, Vehicular Network, ITS, or even pipeline companies. So, the problem with tunnels is that they pose multiple challenges in the communication context. Propagation is highly multipath, extending the communication range in comparison to free space, both affecting the signal with strong failings. Structurally, they are much longer than they are wide. They are uniform and featureless, dark, GPS denied, which makes uncertainty just keep growing the longitudinal dimension. So accurate localization is also a challenge in these scenarios. Our goal in this thesis is to provide some tools necessary for robotics exploration in these tunnels, but in the communications aware context. And to do so, we structure our research in 3 steps: propagation studies in the 2 most common tunnel-like scenarios, tunnels and pipes, navigation techniques to guarantee the connectivity, and at last, localization algorithm. All of this is supported by strong experimental evidence. So let's remember that in free space, an antenna produces spherical waves that propagates with a decay that is inversely proportional to the distance. However, if we put this same antenna inside a cavity, long cavity like a waveguide, then it gets condensed, improving the decay, the free space decay. But as the wave bounces, this causes reflection and failings. To explain this, the rate tracing approach modeled the waves as different rays, which have the same speed, but as they do different paths, they accumulate a phase delay. This causes this constructive and destructive interference and the fadings. To illustrate this situation, we show two waves with the electric field of two waves with different speeds and amplitudes, as in the ray tracing approach. And we can see that this is quite hypnotizing. Despite they move at different speed, when they go through this point, there is always destructive interference, full destructive interference. They have a phase delay of 190 degrees. And in this point, they are always in phase, constructive interference. So the period of this signal, which is a standing wave pattern, it's simply the distance necessary to accumulate a phase delay of 2 pi. In this work, we have adopted the modal theory approach for the reasons you will see later. So each mode is equivalent to a rate in the ray tracing approach. They are defined as the set of solutions to the boundary conditions of the waveguide and describe arrangement of electric fields. They are indexed according to the number of maxima in the transverse direction. So the first mode has 1 maxima, the second mode has 2 maxima, and so on. Each propagating mode has its own wavelength and attenuation rate, and the dominant modes, the so-called dominant modes, are the lowest, or the one with the lowest attenuation rates. In a waveguide, the higher the operating frequency, the higher the number of modes we will have to propagate, and this interaction causes the fading. As in the previous case, we have multiple modes with different wavelengths interacting. So all of this, it turns out that tunnels in a circle are modeled as rectangular dielectric waveguides, in which the wavelength has to be much smaller than the tunnel cross section to achieve communication range in the order of kilometers. This causes several modes to propagate, several interactions causing these fadings. So in the literature, we have the near sector where multiple modes appear, and it's characterized for these fast fadings, and a far sector. Once the higher order modes attenuate, we have the lower order modes interacting, and this causes the low fadings. In the literature, they say that sometimes they are periodic, sometimes they are not. And we are talking about fadings in a spatial domain. This is a signal that is stable in time. So we were wondering, why are these fadings sometimes periodic and why is sometimes not? How can we obtain clean and predictable signals in this multipath environment, which we can use for navigation and localization? Are these fadings repeatable in different domains, space, time? How are these fadings in the cross-section? And how can we exploit this phenomenon? So in order to analyze propagation in tunnels, we have selected the Soncore tunnel, in which our research group has been performing experiments. It's almost 8 kilometers long. It has small emergency shelters and lateral galleries. And to analyze propagation, we use Wi-Fi network cards or continuous wave signal generators and spectrum analyzers as transmitter and receivers. As the platform, Jose Luis lent us this all-terrain vehicle, so we put all the sensor, odometer, lasers, and antennas in the vehicle. So as a first approach, we put the transmitter antenna in one side of the tunnel and displace the receiver up to 4 kilometers. We obtain this signal, which is quite nice. So we observe, as in the literature, a near sector process in which we can see the best fadings, multiple interactions. Then we have a far sector with slow fadings, and in this particular case, at 2.4 gigahertz, we obtain these fadings at a period of 500 meters. So we're wondering if these fadings are repeatable. In the time domain, we use the same transmitter-receiver configuration on different days, and we can see that there is quite good matching between the signals. In the space domain, we use the same transmitter-receiver configuration in different sections of the tunnel. So first, 3 kilometers from the entrance, and then 3 kilometers from the frontier. We didn't want it to cross the frontier. And again, we can see how the signals, the power as a function of the distance to the transmitter, match quite good. At last, we wanted to analyze the link symmetry, so establish bidirectional links in both transmitter and receivers and MOV receivers. And again, we can see how the signals match quite good. So this is good news for our purposes. Then we wanted to analyze the influence of both transmitters and receivers over the fadings. And to do so, we adopted the modal theory. So we modeled the tunnel as a dielectric rectangular waveguide in which the modes have a standing wave pattern in the cross-section. In the case of the Somford tunnel, due to the attenuation rates, we have the first three modes are the dominant ones, and each pair interact and produce a fading structure. So it's quite intuitive that to obtain cleaner signal, you have to minimize the number of modes that interact to two, and that it's accomplished by minimizing the power coupled to a given mode. So in this work, we have selected two positions, the center position that minimizes the second mode, and at 1/3 from the tunnel wall that minimizes the third mode. So we place the transmitter on the side, transmitter on the center, and obtain these two signals. They are just shaped for clarity, they overlap. And we observe that they have different periods. If we go back to the formula of the period, we can see that it depends on the wavelength, and it turns out that in the tunnel, each mode has different wavelength. So in this case, modes 1 and 2 created periodic fadings of 500 meter period, and the first and third created shorted fadings period. On the other part, we place the transmitter in a place in which we have important power contribution of the three modes, and we can see how the signal is not strictly periodic. We have different fadings, different periods, so this is not as predictable as the others. Then we analyze this phenomena at different frequencies. So we can see how at 2.4, 1.8 gigahertz, 868 megahertz, and 43 megahertz. Again, the same two positions, center of the tunnel, modes 1 and 3 in red, and side of the tunnel, modes 1 and 2 in blue. We can see that the lower the frequency, the lower the fading period, and the higher the attenuation rate. The periods match quite well with the rectangular waveguide approximation for this tunnel. Then we wanted to analyze the influence of the receiver position. So what happens if I keep the transmitter in the same position and move it along the cross section? How are the fadings? So we build a route of 12 antennas and cover the tunnel several times to cover the whole cross section. So now we are going to interpret it with the electric field lines. So we see that if we place the antenna in the side of the tunnel, we have the first and second mode. What happens here? In one half of the tunnel, there is constructive interference, and in the other half of the tunnel, there is destructive interference. Remember that these modes oscillates in a wavelength distance, so it's going to be the same in the other positions. We place one antenna in each of the sectors, each of the half of the tunnel, and one antenna in the center of the tunnel. We obtain the same 500 meter period of spatial delay as in the previous experiment at 2.4 gigahertz. And in the center of the tunnel, the mode has a minima, then the third mode becomes observable. But don't pay attention to this right now. So what is important is that the transversal structure is translating into a spatial phase delay between the phases. Here we group the 12 antennas from one half of the tunnel and the 12 antennas in the other half of the tunnel. They are just shaped for clarity. We can see how in the same half of the fadings have in the same period, and in the other half has the same period, and there is a phase delay between both signals. This can be clearly viewed with the upper view of the tunnel, so we can see that this half of the tunnel is in phase and have a phase shift, a spatial delay with respect to the other half of the tunnel. In a 3D space, this is more or less the situation. So one half of the tunnel, the other half of the tunnel, the period is the same in both, and they are shifted. We also see that if we place them then in the center of the tunnel, we have the first and third mode interacting. So what happens here is that in the extremes, we have destructive interference while constructive in the center and vice versa. Again, we place one antenna in each of the sectors and obtain that the center of the tunnel, the sides of the tunnel are in phase and they have this phase difference with respect to the center according to the spatial distribution. So, in the upper view, this is even more clear. We can see how the extremes are in phase and they have the phase delay with respect to. In a 3D space, this is more or less the situation again. So in summary, to obtain clean and periodic phase, you have to propagate or motivate the interaction between just two modes, and this is accomplished via the transmitter position tuning, minimizing the power coupled to the undesired modes. So we chose the center and 1/3 from the tunnel. And that the transversal structure of the present modes, it's actually translates into a phase difference of 0 or 180 degrees in the longitudinal phase. So in this section, we study the longitudinal fadings, preferability, configurations to produce well-defined fadings, as well as the influence of the transmitter and receiver position of these longitudinal fadings. We also perform a study of the fadings in the transverse dimension. So now, what can we use this for? So imagine a search and rescue scenario in which something happened inside the tunnel, humans are not allowed, and what do? You deploy a team of robots and stream data to a base station. For communication purposes, we have a multi-hop protocol developed by Professor Tadeoli that Professor Almeida probably knows. And we already see how to obtain clean and periodic and even predictable fadings. So now we wanted to develop techniques to deal with these fadings. We propose 3 solutions, which are 1D multi-robot deployment, 2D single robot navigation, and spatial diversity. So our goal is to avoid packet loss, and there is a well-known correlation between the received power and the PDR, the packet delivery rate. So if we maintain a link above certain threshold, we have a PDR of 100%. This depends on the heart rate. For higher rates, then you have another threshold, so you have to take this into account. The basic idea is that we set the threshold, and we can see how we have received power above the threshold and below the threshold. So the basic idea was to use robots as relays to go across these fadings. Based on our previous studies about propagation, we have defined some parameters at the threshold, which we set at -70 dBm, peak and valley zones, which are just zones above or below the threshold, and a safe distance, which is the maximum distance that has to be kept between two robots to obtain a link quality above the threshold. So in the deployment algorithm, we have we start deploying the robots. When you violate this safe distance, you set a virtual row between the robots and start bringing them. So when the leader robots traverse the valley zones, the communication is not direct with the base station, but uses the other robots as relays. Once he finds a peak zone, then he groups all the robots and the algorithm starts again. When fading is not found over the threshold, I mean we already know the fading period, so when we don't find a peak zone above the threshold, we set the last leader as a base station and repeat the procedure again. So in this video we have the actual results. This is the robot's position and the link qualities between the different robots. So we can see how in this signal we're looking at the fadings of the leader with respect to the base station and the other link qualities. So we can also see how it's like an accordion. We just bring the robot across the fadings and start again. So in this experiment we had different situations like robot grouping and traversing the fadings, which cause different network topologies. So this protocol favors longer but safer paths, and as the results, the weakest link of the selected path was always above the threshold. So we can say that we have accomplished our goal. Next, we wanted to exploit the transversal structure of the failings, as we saw in the previous chapter. So let's recall that if we place the transmitter on the side, we have the tunnel divided in two. So it's intuitive that we have to go from maxima to maxima, from one half of the tunnel to the other, in slight trajectories. So this may be more clear in this picture, so we would just have to go from one half of the tunnel looking for our maxima. If we place the transmitter on center, then we have the tunnel divided in three, and we have same situation as in the other, or we can do it in one half of the tunnel. First sector, center, first sector, center, or the combination to find possible. This is for clarity, then we can see here how we have to go one half of the tunnel through the other, going through the center, or within one half. So we did some simulations over the real coverage map built in the previous chapter. So we see that if we travel in straight lines in one half of the tunnel or the other, we see these 500 meters failings. If we go through the center, we have the third mode, less failings, but we could take advantage of the failings maximum. So we can see how our zigzag navigation technique obtain the best quality links in comparison to all the other situations. At last, we wanted to facilitate the navigation while improving the communication. So we proposed spatial diversity schemes. Let's remember that commercial spatial diversity, it's made to overcome temporal failings. So they are made in the order of few centimeters, one way. However, in the tunnel, if we want to take advantage of this structure, we have to work in the order of half or 1/3 of the tunnel, which is decimeters per meters. So we have to implement large-scale spatial diversity schemes. In this experiment, we put two antennas together as in the commercial spatial diversity, and the other one far away. So we can see how the two antennas close together have more or less the same information, while with the other we have really different information. So what is actually relevant here is the position of the antennas, not just the separation between them. So we consider the case of having two halves of the tunnel, and what is relevant in this case is to keep one antenna in each half of the tunnel at all times. Here we can see how each signal will perceive the failings going below the threshold, but if we take the base of 2, we are always above the threshold. So this is actually an experiment from last month. We did, instead of hardware spatial diversity, we implement one base station and two transmitters in one dimension, and they use each other as relay throughout processing. We have presented also a 2D single road navigation exploiting this transversal structure of the failings, and implement large-scale spatial diversity schemes designed for this tunnel environment. Now we move into pipes, which is one of the other common tunnel-like environments. Actually, this was during a research study at the University of Pennsylvania. They had a project for dam pipes inspections, and they needed to localize the quadrotor inside the pipe. So the problem with these scenarios, as we mentioned, is that they are much longer than they are wide. They are featureless in both vision and texture. They are repetitive, dark, slippery, so if you use wheel robots, the wheels will tend to slide, and they are GPS denied. So all of this really hinders the accurate localization. Here we can see an example how if you have just straight lines, the uncertainty in the longitudinal dimension just keeps growing. So I will just give you a hint. We want to use these failings to localize, but they were not previous literature about propagation in pipes with this end. So we faced the challenge of adapting what we have in tunnels into pipes. So we first analyzed the theoretical aspects of propagation in pipes, and we can see that again we have TE and TM modes. Each one describes geometrical arrangement of the electric field, which in this case it's beautiful. For each mode there is a cutoff frequency, and it propagates if we chose a frequency above this mode, and this is quite an advantage over tunnel, because remember that in tunnels you have to work at high frequencies for them to behave as a wavelet. Here we can just choose how many modes we want to propagate. Each mode has its own wavelength in the waveguide, which is different from the free space, and an intuitive idea, it's going to happen the same as in tunnel. If we have more than one propagating mode, they will interact and cause these failings. So to test these concepts, we chose 3 scenarios. At first, a small light pipe. We use a continuous wave generator as transmitter and a handheld spectrum analyzer placed on a Lego car as receiver, and just displace it inside the pipe, and a laser pointing to the car to obtain the position estimation. The real scenario, we have the Santa Ana Dam in Castellón Roy, Spain, and the Alatuna Dam. They are 4 meter and 6 meter in diameter. We use the continuous wave generator and spectrum analyzer as receiver, and this time we made the measurement with humans and used plasma as ground truth. So the procedure again was to place the transmitter in one extreme and displace the robot inside the pipe, measuring the received signal. So below the cutoff frequency, you choose a frequency which is below the first mode, the first propagating mode, and we can see that there is a rapid attenuation. The pipe does not behave as a wavelet. Then we selected a frequency between the first and second mode, so we are just propagating one mode. This is used for communication purposes because you obtain a clean signal with no failings, but this wouldn't be useful for localization. There are some approaches that uses the slope to localize in these scenarios, but the problem is that in metallic pipes the attenuation rate is of few dB per kilometer, so you wouldn't be able to obtain it. So then we selected a frequency between the second and third mode, propagating the first 2 modes, and we observed that the interaction produced these periodic failings. These are a function of the diameter of the pipe, the cutoff frequency, which is fixed, and the operating frequency, which we can vary. So compared to tunnels, we can see how in tunnels we have this linear sector because of the interaction between the propagating modes, while in the pipe the signal is quite clean because we have just 2 modes interacting. Then we studied that the interaction between the first and third mode, as in the case of the tunnel, will cause shorter period failings than the first and second one. The problem is that when you propagate the first 3 mode, you also propagate the second one. So how can we get rid of this second mode? And we find the answer by analyzing the structure of the electric field. So the second mode has radial symmetry. We observe that placing the antenna perpendicular to the electric field lines, and in the center the right contribution will null the left contribution, while in the third mode we have constructive interference. So in this case we selected an horizontal orientation for the transmitter, and we observe that we obtain shorter period failings. So to illustrate this situation, we have same operating frequency, same antenna position, but different orientations. We can see how if we put the antenna vertically oriented, parallel to the electric field lines of the second mode, then the bimodal propagation is dominant, and we have here the third mode interacting. On the other part, if we place the antenna in horizontal orientation, then we annulate this effect of the second mode. As well as in the tunnel, we wanted to analyze what happens with these failings if I move in the cross section. So by analyzing the electric field, we observe 2 cases, upper and lower half and left and right half. Analog to the case of tunnels, we analyze the constructive interference through the electric field lines and observe that in the upper and lower half we have constructive while destructive interference, and vice versa, and this causes this spatial phase delay between the phase. If we place the antennas in the right and left half, we always have constructive or destructive interference at the same time, so we have the failings in phase. So in this section, we analyze metallic pipes with emphasis on the periodic fading phenomena and study these fadings in the transverse dimension. At last, we said that we wanted to use these fadings to localize. As they are periodic, repeatable, and they are clean, then we propose to an RF odometry-like method for localization. So it's a discrete algorithm in which we just traverse the fadings and count the maxima and minima that has been traversed. So the trigger would be the change in the slope. This would give us a localization resolution of 1/2 of the period of these fadings. That's what we wanted to reduce the fading period as much as possible. So to analyze this algorithm, we use again the label card inside the pipe and the laser sensor pointed to the robot to obtain the distance between the robot and the extreme of the pipe, or the position estimation. We did some forward and backward travel several times, recording the received power. And in this particular case, the computations were made online. So what is important to say here is that we have two delays. One is associated to the moving average filtering. Although the signal is clean, we wanted to obtain a really clean signal, so we just added a 10 samples moving average filter. And there is another delay associated that to perceive the change in the slope, you have to traverse the fading. So actually, you know it after you traverse it. As the fadings are stationary, there is no cumulative errors as in other methods like odometry. And the maximum error here occurs when you almost reach a fading, but you don't get to the change in the slope. So you don't get triggered, and it's 1/2 of the period of the fadings. So to test these concepts on a more real scenario, we bring, with help of Professor Tucci, the Pioneer, into the pipe, and we added structural landmarks each 10 meters. This was used to obtain a position estimation and jump route for comparison purposes. So we can see how after 70 meters, the odometry accumulated a 6% error, while our method just 0.9% after the trigger. But we wanted to exploit the spatial diversity here as well. So we can see that if we have one receiver in the upper half of the tunnel, while other in the lower half, we will have delayed signals, and we can add two more triggers where the signal cross each other. So this would allow us to improve the localization resolution, and we can see how there are the two signals. We have much more triggers and much more localization resolution. Courtesy of our friends at UPenn, they implemented a visual odometry algorithm inside the pipe. They went 15 meters forward and backward, and we can see how in just these 50 meters, they have an accumulated error of almost 5 meters, which is 30%. So we wanted to contribute with them, and it turns out that pipes inside dams have different characteristics. So they have elbows, and they have one enclosed, which is the penstock that prevents from flooding the pipe. And we wanted to analyze if our method would work in this situation. So we use several vane pipes with different elbows, 90 degrees, straight pipe with 90 degrees, a corrugated pipe that is used for fan structures with 90 degrees, 90 plus 90 degrees, and 90, 180 plus 90 degrees. So we can see how in all the cases, the phase of the period of the phase is maintained before and after the elbow, and they match the theoretical period of the phase. It seems here that this phase has a much more special period than this one, but no, it's because in this one we had less distance to cover, so it's the same period. And as for the closed end, we actually see the opportunity to use a standing wave pattern due to the monomodal propagation. So if the extremas are open to air in monomodal propagation, we have just one signal with no interference. The thing is that if we close one end, then we have an incident and a reflected wave, and it causes these fadings. So we can see how actually in this case, the standing wave period is shorter than the case of bimodal and trimodal propagation. So we could improve the localization resolution even more in this case. To close the loop, we go back to tunnels because this could help us to localize in the tunnel as well. Actually, the only reason why we could localize in the Sunport tunnel is because we have lateral galleries each 25 meters, which are really characteristic of the Sunport tunnel. I haven't seen this characteristic in other tunnels. So the problem in the tunnel is that we have more modes interacting and the signal is noisier. So a simple changing the slope wouldn't work. So we did our first test here, placing a receiver with an onboard computer on an X-rotor and travel a distance of 550 meters, recording the received signal. We can see here how the signal in both experiments match with the simulations of the same signal propagating in a rectangle using the rectangular waveguide approximation. And they match quite well. So this makes us believe that if we include these simulations using a particle filter approach, for example, we will obtain good results. The last question would be, how can we determine the fading period before entering the tunnel? In the pipes, it's quite straightforward. You have the diameter, you know the frequency you're going to work, and you obtain the fading period. In tunnels, what they do in the literature is they do a measuring campaign, they find the attenuation rate, and that gives you the dimension of the equivalent rectangular waveguide, which is not the same as the real shape. So in an emergency situation, you will have no measuring campaign available. I mean, besides the Sunport tunnel and Golden tunnel, I don't know if they have these measuring campaigns. And on one side, the finite element method has been considered memory demanding and time consuming. However, we found that the propagation constant, which translates into the fading period, can be obtained through a 2D analysis, just with the cross-section of the tunnel, imagining that the tunnel is regular. So we use the actual profile of the Sunport tunnel, placing a laser sensor on the floor, and results from other tunnels from the literature. So we can see how we compare the experimental results, rectangular waveguide approximation, and the finite element method solutions. So we could see that actually the finite element method solutions are more accurate than the rectangular waveguide approximation. So this is quite a big advantage because it means that you can get inside the tunnel, in the entrance of the tunnel, place a laser sensor, scan the cross section, and you know how will be the fading period. So in this chapter, we present a localization techniques that offers an alternative to standard techniques by means of exploiting these periodic fadings, and we validate the rectangular waveguide approximation. So to summarize, in tunnel-like environments such as tunnels, pipes, communication range is extended, but signal gets affected by strong fading phenomena. These fadings are caused by the pairwise interaction between the propagating modes. In the case of the tunnel, we modeled it as the electric rectangular waveguides. They have no specific cutoff frequency for each mode, and you have to work at high frequencies to obtain this waveguide behavior. This causes much more modes to propagate, which causes the near sector and the signal is noisier. In pipes, the other part, they are metallic cylindrical waveguide, which has a cutoff frequency for each of the modes, so we can select which modes to propagate. The same already mentioned, we work at much lower frequencies, so we have much shorter period fadings. To obtain clean and predictable periodic fadings, we have to motivate the interaction between just two modes We accomplish this by maximizing the power to the modes we want to propagate and minimizing the influence of the other modes by tuning the antenna position in both the tunnels and pipes. The present small structure, once they propagate, they determine the phase difference of the longitudinal fadings. So in summary, you want to determine which mode to propagate, which determines the fading period due to the transmitter position and the operator frequency, and the spatial phase difference between the received fadings is given by the structure of the holes. To guarantee network connectivity or to improve the link quality in this scenario, we have, depending on your available resources, we have proposed three solutions, which is multi-robot 1D deployment, single robot 2D navigation, and spatial diversity schemes. So in the 1D navigation, we have a team of robots traveling in a straight line, like an accordion. They work like an accordion and use each other as relay to go across these fadings. As you are traversing the fadings, you could use them to localize. So we have to implement this part. For the 2D navigation, we have one single robot with one antenna, and you have to do this zigzag path depending on your transmitter setup. Spatial diversity schemes, we propose large-scale spatial diversity scheme in which what is relevant is the position according to the propagating modes. And again, as you are traversing the fadings, you could use them to localize. So in this approach, you can use the fadings to localize while keeping the link quality above the threshold. As for localization, the fadings are periodic, repeatable, and predictable, which makes them suitable to localize. So we have proposed an error photometry-like method, which is a discrete algorithm traversing the fading and counting the number of maxima and minima. And we can use also this method to reset the errors accumulated by other techniques, such as visual or wheel odometers, or even an IMU. So this would be an intratunnel equivalent to GPS plus IMU systems. In pipes, we can use bimodal or trimodal propagation to produce these clean fadings. The fading period is previously determined with the pipe diameter and the operator frequency. That's all you need. We have exploited the transversal structure to improve the localization resolution, and we have made an extension for dam pipes in which we study bent pipes, the period is maintained, and we can exploit the standing wave. At last, in tunnels, the signal is noisier, so we have to work in a continuous approach, which we believe we can make due to the agreement between the simulations and the results. The fading period using the finite element method could be obtained by placing a sensor in the entrance of the tunnel, the laser sensor, and the fading here would play the same role as the periodic emergency shelters. So this sentence more or less summarizes all the work. So all the fadings in these confined environments are unavoidable, and they are usually considered a serious problem for communications. We have shown an interesting way to address this issue by generating and detecting non-geometric periodic fading structures. We have also demonstrated how to navigate to deal with these fadings in a communications-aware context, and how to benefit from their periodicity to localize in these challenging environments. So as a future work, we are already implementing the particle critical approach in collaboration with Innova, obtaining good results. Localization in tunnels is just proposed by the moment, but we believe that this same approach would yield good results. And also, if we change the antenna polarization, we have to shift all this presentation in the other dimensions, so we could use flying robots to exploit this diversity. So about the challenges we have faced in this thesis, we have gone 12 times to the Somport tunnel, which is 170 kilometers from the university. It's hostile like the moon, really, really hostile. It's dark. It's really cold all the year. It doesn't matter if you go in winter or summer. It's going to be always 5 degrees. And we have to do some paperwork. It takes 4 persons per hour to instrument the vehicle. Just imagine putting some little screws with the cold gloves and inside the tunnel. Loading the vehicle plus traveling plus instrumenting twice takes 8 hours to get just 3.5 hours to 4 hours of experimentation. And I would like to personally thank Jose Luis and Paco that allowed to do all this stuff with this vehicle. We started with the laser and an eye odometer, then we moved to a more accurate odometer. The same with the structure in the antenna. We started with 1 antenna, 3 antennas, then other RF modules, and finally the rack with the 12 antennas. We are also going to the Santa Marta mine, which is 360 kilometers. This was the opposite, was very hot. We have to carry all the material to the mine, and it was 3 days of experimentation. We didn't mention it in the work because we did coverage map in a really near sector. So we observed this fading, but they were fast vegetated in the near sector. We have gone also, I won't say the word, but thanks to Professor Bucci that he carried the Pioneer in his bag and left his bag inside the pipe with this. The problem is also that they do service outage only 2 months in winter. I mean, we cannot sacrifice agriculture for our research. And if something goes wrong, you have to wait until next winter. But don't worry, because winter is coming. At last, we have gone 1 time to the Alatuna Dam, which is more than 7,000 kilometers from here. This is a hydropower station which gets a service outage only 3 days in 6 months to 1 year. So why we wouldn't implement still our algorithm is because the first trial was August 2013, in which we made these propagation studies. Second trial, October 2014, it was postponed by the dam crew. Third trial, April 2015, just 3 months ago. But the people from UPenn broke the quadrant before going to the dam, so it was suspended, and it seems to be like our 4th trial will be August 2015. Here again, the paperwork, I mean, it's United States, it's even more complicated. This dam in particular is under jurisdiction of the US Army Corps of Engineers, so I had to go through a visa check, security clearance, and actually we had the permission to go inside the pipe the day before we went. And we had to pass a security course and a written examination with 50 questions to be able to get inside the pipe. So we have published all these results in relevant journals and conferences in both robotics and communications, which can be summarized as 1 accepted journal and 2 under review, 5 conferences, 4A and 4B under review, and 1 under review, and 1 accepted commercial and 1 under review. So in summary, this was a 4-year PhD from July 2011 to July 2015. It has a strong experimental work. I mean, you have seen how many times we have gone through these scenarios. 2 research stayed at UPenn, 6 months and 1 month, on the advisory of Dr. P.J. Kumar, and 1 presentation award. So thank you very much, and I really enjoyed with some videos of rappelling, trying to get in out, because the problem was not just to get inside the pipe with the robot. Once we were inside, we saw that the problem was going to be to take him out, so it's not really long. Okay, here. This is us trying to take the robot out of the field. So thank you very much, and I'll be happy to answer all your questions.
Okay. So thank you for the presentation. Let's go to the questions and comments from the members of the committee. So, Luis.
I congratulate to you and your advisors for the theoretical contributions, strong experimental contributions, a very complete work. You know how in this group appreciate the experimental, we appreciate the experimental, the experiments in real environments, very difficult environments. I have a few questions. The first one, when you use the rectangular approach to predict the propagation in the tunnel or pipe, the tunnel in particular, how do you fix the best parameters, dimension of the rectangle, in order to get the best prediction which match, better match with the experimental measurements?
The thing is, in this work, we are working with vertical polarization. So this term gets null. So by knowing actually our approach was more by taking a look at the fading period instead of the attenuation rate as in the literature. So we obtain the fading period, and with the fading period we can obtain, and knowing the working frequency and the modes that propagate, you can obtain the width of the tunnel, and by having the width with the attenuation rate, you can have the height of the tunnel.
Regarding the problem of localization in tunnel, how do you solve the problem of localization in the first part of the near sector, in which the shape of the way is very noisy? It's difficult to obtain the localization in this 500
messy near sector. Okay, let me go. So it's known that higher operating frequencies are related to a higher near sector because we have much more propagating, while lower frequency signals have a really short near sector. So what we propose to overcome this problem is to use two signals. So you can use, to cover a large area, a high frequency signal which has an associated long near sector, but we could use lower frequency signal to localize within this near sector. After you overcome the near sector, then you can localize with the higher signal frequency.
Okay. And in the far sector, in the slow fallings, why you cannot use the shape increasing or decreasing value of the signal to obtain a more precise localization, lower than the half period?
Yeah, actually
this signal you can filter more or less this.
Yeah, actually the half period of the fadings in tunnels, we have much longer distances, so we will have a poor resolution, and you have this false positive which will enter this algorithm. So what we are working on right now with people from Nova is implementing a particle filter that uses the propagation model to fit the data.
Okay. Thank you. No more questions?
Thank you.
Congratulations.
Thank you.
Okay, thank you again, Professor Luis Almeida.
Thank you very much. Yo creo que me van a perdonar por decir solo unas palabritas en español para agradecer la invitación y decir que es siempre un placer muy grande venir hasta aquí y ver el trabajo bueno que se Y bueno, dicho esto, pues cambio al inglés porque es la lengua que ahora es como el esperanto científico. Y como yo he dicho muchas veces a compañeros míos ingleses y americanos, que esto no tiene nada que ver con un reconocimiento de superioridad de su cultura, es solo porque es un medio de comunicación actual y por eso es muy bueno que nosotros lo hablemos también para facilitar la comunicación, solo por eso. Bueno, tenemos muchas lenguas, ese es el problema. All right, so switching to English now. So let me say, just I also I end up always doing maybe more questions than what I should. So if I go over my time limit, so please tell me, and I will just stop at some point. But let me just make some comments in general first, and then I will ask just a few questions. And the first comment is the following. When I started doing the thesis, I really enjoyed it. I enjoyed it so much, really, because I think that you did very well when you, in the introduction, when you added this section on telling the story. This was so nice because it really creates immediately a good feeling, because you tell how the problem was found and how then you worked out the problem and how then you made use of what you found so that you could actually use it for something like in practice, yeah. Right? So this was very nice. And then of course when you go through the thesis, it's even nicer because I mean it's probably one of the best written English thesis in English that I've read. I mean I found maybe 3 typos, which is something unbelievable. The only thing I found several times, which is interesting, is some wrong references to figures. So it seems that you have probably copy-paste in some places. And so there are a few places where you're referring to the wrong figure. But it's, I mean, it's beautifully written text. So I'd like to congratulate you on that. And then going through the work, it's really nice to see how you go to the measurement campaign, so you get actual data. Then you try to see in the literature what are the available models that could be related. Then you get them and then you do this identification to match the models on the data, and then you come up with models that are accurate in these scenarios that we all know are tremendously noisy. And so this is very nice. So anyway, I see here 3 different contributions. I see a major contribution, which is all the work on radio propagation and the modeling of radio propagation. And then 2, let's say, less important contributions in terms of the amount of work that you did. One still more relevant to me, which is the localization, which I think it's really nice.
Actually the newest.
Yes. And then finally the one with the navigation, which I think was not as much worked out. And probably there's much more work to be done yet in that direction. So let me ask you one thing that I already asked in previous times that was here. So what is, to you, this is something that was still missing there in the introduction, what is really the thesis? So what is your statement that you are then going to prove?
Okay, the thing is we wanted to navigate in tunnels under connectivity constraints. Mm-hmm. So based on that, we have to study propagation. Once we find this, okay, we have this periodic and predictable fading structure, so we can deal with it. We came out with this algorithm, with this accordion algorithm, and later on we could see that because in that part the localization was with a previous map. Then we discovered this localization with the pipes, are thinking about it to adapt it to tunnels, and so we could localize. So in few words, we wanted to develop tools that you will need to do this exploration in tunnels under the connectivity constraints.
So the statement, the thesis is a statement. You say this, and then you are going to prove it, right? So as a statement, it would be something like that it is possible to accurately model the radio propagation in tunnels so that it can be usefully applied to localization and navigation. Something like this word. And it's a pity that it's not there, right? It's okay. Just thinking in this way, so how we, in a sentence, we state our purpose, research purpose. Our research question is normally a good exercise. But still, I mean, it's a minor thing. Now, let me ask you just, you were actually saying about the localization and the navigation, and this is something that I felt at the end was, of course I cannot say missing, because the work is very round as it is, very nice, but of course, as a normal research work, it opens up many issues. But there's one that I felt, so you have this navigation where you use distances, right, for the work of the algorithm. So you need to localize.
Yeah.
Right? So you use everything else to localize except your own developed localization method.
Yeah.
So at the end you develop your localization method. So why didn't you, bring it back and show the navigation algorithm working with your localization method?
Basically, time constraints.
All right.
I mean, we have gone to the tunnel several times. In the pipe, we could go each winter, so we could develop the localization algorithm. We finished on October 2014, so we didn't have time to go again to the tunnel with all the robots. And I mean, it's not just my work. We need plenty of people to go to the tunnel. Domenico, Luis, Danilo. So it's really a huge amount of work to do one of these experiments. But basically, just lack of time. But we will do it. We will do it.
All right. All right. No, but because I mean it makes sense, but it's clear that it will be done at some point. So I think it was more or less clear. So in this, let's say RF photometry method, which is pretty cool, I would say. There is also another issue that you always say as future work. And again, it's something at the end that we are waiting for it and future work, which is the filtering. Of course, I also understand that it's a different topic, but it's kind of a pity because this would really close it up so that you can filter and then match. Like I don't know why do you prefer the particle with respect to the Kalman filter? I think it's
because in the particle filter we are actually using this signal as the map, and we are working in 1D dimension, so it fits quite well to the description of the particle filter to use it in this situation.
But if you have some measurements, you can get some idea also of all the covariances, and you can come up with a good model for the Kalman filter.
Yeah, as well.
And I thought it would be then at runtime easier to use, or at least fast. I'm not sure.
No, I mean, okay, I didn't put it here. We are working with Teresa and Jesus from Innova implementing the particle filter. We are already getting good results with this in the pipe, with real measurements in the pipe. And I think if that's not good for ICRA 2015, you will see the results. We already obtained quite good results with this.
Good.
But
how long does it take? How fast? So can you do it on one?
No, right now it's offline. What we do is we record the data.
Yeah.
We go into a file and process the data. We still need to implement this online approach.
So this reminded me, of course, what you have is a structure, right, with variations that allows you to do a relative displacement. So at the end, it's a relative localization.
Yeah.
But of course, you talked about one of the issues is cycle sleeping, right?
Yeah.
So you can, and then this builds up some inaccuracy that you will have to sort out some other way, right?
With the particle filter as well.
All right. And
I'm aware of that problem. I mean, we did this considering that the signal is really stable inside the pipes. I mean, there is a Faraday cage effect, so you don't get external interference, and the signal is quite clean. We apply this RF photometry and obtain quite good results. But in more noisy situations, yeah, we have to go to the particle filter and use
all right. And if there is a fault in the robot and it has to reboot, it will probably lose the original reference, and then it will be a bit messy. It reminded me of the old lifts that when the lights were off, then they would have to go down to the bottom or to the top to calibrate, and then they would work again.
Yeah, this is why we call it RF odometry, because as well as in odometry, you are referenced to the point you start. So.
But would it be possible to come up with a scheme that would provide you absolute localization? By, for
I see
example,
that.
using multiple frequencies at the same time.
Yes, yeah, of course. And actually in tunnels, I see that more feasible in tunnels because the attenuation rate is higher than in. And let me go for a slide. So what we were saying, you were saying more or less this. We propose multiple structure for a more robust localization. So in this case, we would use both transmitter position that we study in this work, and by multiplexing at the time domain, you could perceive with just one receiver both structures.
And using that figure, it's one thing that bothered me. How do you easily, in an automatic way, separate the near from the far sector? Because it's kind of foggy, right? Or fuzzy.
Yeah. We still have to work on that because it's actually, you could analyze the signal. The near sector has these fast fadings, so you could analyze how many, like a zero crossing, how many variations are you getting in a period of time, but yeah, it's still diffusing there.
So another potential application that came to my mind as I was reading, there were some similarities with some modulation techniques, like for example OFDM that allows us to send multiple beats at the same time. That's why we increase the beat rate, because it uses several carriers that when they are convoluted with the beat width, and so it creates a sync, and then they are displaced so that the zeros of ones are on the maximum of the other ones. So I was wondering whether you can have multiple communications at the same time just by adapting the position of you could, for example, put several robots along the way, and in a way so that some robots will communicate with a transmitter, other robots will communicate with another one. Maybe they can also switch, but these could create the parallel channels so that they could communicate in parallel at the same time by putting these where it's zeros for one, it's maximum for the other one. Would this work? I mean, this could also be interesting. I don't know.
Yeah, I didn't think about it. I appreciate for your insights, and yeah, that's something we would have to evaluate and see if this would work in the company.
Let me ask you something completely a bit different now. So on the mean side, to be a bit mean. So I really like this. So it's very well motivated. So you constrain your work to radio frequency, right? But there are other approaches, right? So you could, for example, use ultrasound to do ranging.
Yeah.
Right. It will work. But what could be the pros and cons with respect to this?
I mean, we did this approach because you just need one receiver. I mean, with just one transmitter and one receiver. That's why we put in the last experiment, the explorer in the tunnel. We put the receiver in the odometer because we didn't have laser, we didn't have a odometer, wheel odometer, they're not feasible for explorers. So we only needed an IMU to discern the direction we were moving. So, I mean, this is like, with just an RF transmitter and receiver, we are accomplishing all this.
All right. So one thing that also supports
the whole cross section, we analyze the antennas close to the galleries compared to the center and the other wall, and we see no important difference between each other.
So that was amazing, and so it's another question that I'd like to ask you, which is basically, what are the constraints of the tunnel so that you can apply your technique?
Okay, it has to be regular. I mean, tunnels have irregularities. The important, as well as in pipe, is that the diameter of the shape is maintained, because if it's changed, then the fading period will change and you have another different situation. So maybe you could use a laser sensor grabbing the cross section, and if you see a change in the cross section, then you could use it in the modeling.
All right. But so I was expecting, let's say, more dependence on the let's say, the properties of the walls. For example, if they were really plain, or if they were very irregular. But it seems that that's why I was
No. In this soil, we have sections that are really smooth, sections that are irregular, but the scale of these irregularities compared to the wavelength are not quite important, so they don't influence.
Yeah. So that's interesting because it really improves the applicability to your method. Because I would expect that many tunnels have very rough walls. Well, let me ask you just one question more to finish so that I will not extend more. I really appreciated the discussion with you that we had. So you say in the future work that you would like to do this now with aerial robots in this case, so quadrupeds or something like this. So what is really the difference? So what do you expect to be different with respect to what you did?
Okay, the difference is if you see the phase period formula, I can. Okay, well, just with this one. When you use vertical polarization, the phase period depends on the left and right wall. When you use horizontal polarization, it depends on the height of the tunnel. So as the shape is irregular, we expect more irregular phase in this using this configuration.
So it will be, but more beneficial or less so? Because that is probably not the only difference, right?
I think it's going to be, we'll get worse results in using this.
So what do you gain by using them?
Maybe it's your only option. You have your entrance blocked, you cannot get in with run robots, and you just have to use a quadrover.
Thank you very much. Thank you. I appreciate not only the thesis, but also the discussion.
Ok, thank you very much. Bueno, empiezo también felicitando al doctorando por el trabajo y el trabajo experimental, además trabajo experimental de campo o de túnel o de sitios en los que normalmente se consideran que no son los más cómodos para hacer experimentos. Y también, bueno, pues felicitar a los directores, en este caso además hay que decirles que bueno, han contribuido de forma importante a los experimentos, suministrando al menos los equipos, los coches. Tremendo, ¿eh? O sea, yo, de alguna manera, ni siquiera lo has alquilado, sino que ha utilizado los de los directores. Muy bien.
Sí, amor por la ciencia, por eso yo agradezco a José Villa Paco que nos hayan dejado su vehículo y nos hayan permitido inclusive taladrarlo para colocar el láser, los botones. Amor por la ciencia.
Sí, entrar en los túneles con el Pioneer a cuestas, esto también es la nota. No lo había visto, está por aquí, ¿dónde está? Está tremendo, vamos. Esto ya es para nota. Entonces, pues también enhorabuena. Y enhorabuena al grupo y al departamento, siempre es un placer venir a Zaragoza y siempre para ver buenas tesis, con lo cual, pues, enhorabuena al grupo y al departamento por las buenas tesis que presentan. Esto de entrada. Después la segunda consideración, claro, es cuando cada vez que me hago mayor, pues ahora siempre soy el presidente, y lo que pasa con eso es que todas las cuestiones que tenía, absolutamente todas, han sido preguntadas ya. ¿Ah? Todas, ¿eh? En este caso han sido todas. Bueno, está bien, también significa que pensamos lo mismo. A ver cómo improviso algunas. Now let's switch to English.
Okay.
Well, my question will be not, well, let's say target, the first or the previous one. So let's go for a more global question in the first part, propagation. I'm not expert in propagation, but in any case you describe a world, a particular environment in which you do everything with omnidirectional antennas, you do everything with 802.11, 2.4 gigahertz. This is a particular experimentation setting. What about other technologies, even in wireless? First,
I mean, we chose these frequencies because they are in the, most of them are on the ISM band. So you could get transceivers at this frequency for relatively low price. So 433, 868, 1.4, and 2.4. We also did an experiment at 5.2 gigahertz. The problem is that you have much more modes propagating. So the near sector it's more than almost 2 kilometers. So you have to cross the frontier to observe these readings.
Omnidirectionality of the antennas. So you use always these omnidirectional antennas. But what matter if you use other kind of antennas?
Well, actually, yesterday we were calculating if you use a really directional antenna to avoid this multipath, and the gain is in the order of 10,000s the power to obtain the same range as you obtain with the multipath. So we are taking advantage of this multipath.
Yeah. Good. Okay. Next is okay. In the same sense, the effect of you have seen this car. Okay, I assume that this is also an effect in this propagation. The cars, trains, everything inside the tunnel will generate metallic objects effects. Did you try to analyze in some way these effects?
Yeah. Actually, in some of the experiments, we have gone with 3 cars, Jose Luis, Paco, and another friend, and we place the cars in the lateral galleries. So in the part of the tunnel with the lateral galleries, and we see again no important significance. If you block one section of the tunnel, what is going to happen is that at the moment of the impact around this area, you will have power transfer to higher order modes. You will have again a near sector, but this will diffuse really fast. So you will have again these fast readings.
Okay. Okay. This idea of, well, okay, I understand that the effect of you first explain this navigation and later the localization, okay. But for navigation, some of the things that you did was, okay, at least a little bit, okay, for navigation you have to know the position of the others, right?
Yeah.
And then you do not apply the result of the localization. So
no.
in a way, you just use some kind of filter. By the way, I have been trying to do similar things with filtering techniques, and I have to say that because it's not Gaussian, this Kalman filtering approach gives a lot of problems, and I obtained better results with the particle filters. Okay, if you fix the distance, for this fixed distance, it's Gaussian. But if you move, this is not Gaussian, no longer Gaussian. So you need this very significant advantage of using the particle filter, but you use it, the Kalman filter in this navigation experiment, right?
Yeah, I mean that's not my work. Another student, her PhD was about this localization using SLAM, and what we did is build the map of the tunnel, and we are localizing over this map. The thing is, we can localize because of the periodic emergency shelters every 25 meters. And that's what shrinks the uncertainty. If not, we'll have the uncertainty growing in the longitudinal dimension.
Yeah, that's true. But in any case, you need to know the position of the other. But okay, again, is the result that you present in the last chapter.
Yeah, the thing is, localization is the newest.
Let me propose you your activities in the future. Going towards the, let's say, fading base SLAM, right? Why not?
Okay.
Fading base SLAM could be something that you can do. Why not? You can interact with some people here to propose this. Why not?
Of course.
Because you have to go back. And then localization for navigation. So you put localization in the last chapter, and then you immediately say, oh, okay, now this is the last chapter, go back. But this is another thesis, I understand. This is good enough. Okay, but anyway, I would like to, just 2 words, no one but 2 words, ground through. In many cases, I would like to see the ground through. You compare with the simulation and the real measurements. What about the ground through?
Yeah, it was, the only experiment that doesn't have the ground truth is the X-rotor, because actually we didn't have the ability to put a laser or other sensor to give the time-to-time distance.
It is not very difficult. You can put some kind of lasers. Why not? If you put the robot inside the tunnel, I mean, you can also contact it.
I mean, right now the X-rover has no lasers, so.
I see. Maybe some sensors in the market that can triangulate and compute the positions.
Yeah, we can do this.
Anyway, this is a recommendation to publish your papers in Q1. Q1, experimental result to validate, because this is an obvious question from the reviewers, right? This is, I would put this question. What is the ground truth? And by the way, it is not clear enough for me in the motion of the multi-rotor system. I propose don't ask about the multi-rotor system. But anyway, I will ask something. So what about the, okay, you put this, okay, there is a manual navigation, right?
Yeah.
And you say that this is in a straight line, okay?
Yeah.
I know good pilots, but in a straight line, it's not a straight line. So where do you know where is the quadrotor?
No, actually, I mean, if you see the video, let me go back.
You can talk about the IMU, but I mean, I know the IMU.
Just to mention, I'm quite good pilot, so we try to, I mean, you can see in the video, we did not distance from the X-rotor more than 3 meters, and what I try to do is to keep the quadrotor in the center sector. I mean, we propagate the first and third mode, so we have the tunnel divided in 3. I just try to keep in the center sector. That's it.
Now this is not in the same. The two people running at the same time that they are should be very good. Anyway, ground truth is important. So this is just last question. So in my opinion, let me repeat again that I enjoyed the thesis. Also the presentation was good. In addition of the manuscript was also very good, the text. So I agree with you that it is very well written. And then congratulate again for you.
Thank you very much.
Now, I think that the question was if there is somebody in the room. So, ¿hay alguien en la sala que quería hacer alguna pregunta? Doctor, tenía que ser doctor. Si no,
Sí,
no,
tiene que ser.
no vale. ¿Algún doctor en la sala que...? ¿No? Bueno, pues entonces hemos terminado la...
Lo dejo por los vídeos.
Sí, estamos más.
Aquí, que es sobresaliente. Posteriormente se comunicará lo que hemos votado en el sobre ese que es confidencial. Enhorabuena por tanto.
Muchas gracias.